Good day. We're here to present our research work titled Investigation and Modeling of an Economical Viable Energy Storage Solution for an Off-Grid Hybrid Renewable Energy Systems of a Town in Northern Nigeria. It was presented by me and my colleague, and my name is Mayowa Alonge.
I am Emeka Ugwemaju.
And this research work is also supervised by Professor Moshin Jamil. So this is our table of contents. Table of contents shows everything that is involved in this slide, and it starts from the introduction, research methodology. Research methodology has subtopics under, as we can see, then conclusion and references. So this is our introduction. Now, in remote areas such as northern Nigeria, inconsistent electricity supply poses a problem for socio-economic growth. World Bank and National Bureau of Statistics stated that Sokoto has the highest rate of poverty in Nigeria, standing at about 85%, at 0.409 and 5.81 million impoverished. Sokoto State ranked on the conditions with the highest multidimensional poverty index. So due to this factor, we thought of designing an hybrid energy systems that will solve the problem and make life better for the communities, and also other investments that is located in the community. So moving on to the next slide. This is our research methodology. Our research methodology includes project definition, which we have done earlier, site assessment and selection, load profiling, renewable resource analysis, determination of storage technology, system modeling using OMA Pro, optimization and simulation analysis. Then it also involves the financial analysis, then the reports and implementations. So to the next slide, this is the site selection. Wamako is actually located in northern Nigeria, and they experience dry season, making it an ideal candidate for installation of hybrid renewable energy resources. This region also faces challenges related to unreliable electricity, contributing to elevated poverty rates. So to address this issue is one of the, like I said earlier, one of the reasons we are actually focusing on these communities, because we want to address the issues of this electricity deficit that they are facing. Yes, they have a lot of investments like National Youth Service Corps is located there. There are other small investments too, like amusement park. So, but with all these things, they still experience epileptic electricity, and because of it, we want to design a hybrid solar system. That's why we decided to focus our attention on Wamako. So, moving on to the next slide. Now, this is our load profiling. What does load profiling mean? Load profiling means that we have to calculate the minimum load that each household is going to consume. So, and based on the research and data that we gathered and calculating the minimum, we decided that there will be light, fan, TV load, and each of these has the DC light has 25 watts, the fan 50, the TV load 25 watt as well. So the total is written here, which is about 125, and also there is energy loss, which is about 5% of the total. And then the energy required by each household is also stated here. Now to my right is the Wamako town load profile, which runs from 0 hour to 23 hours. So on 0 hour, it can be shown that fan is on, is consuming 50 watts. At the same time, there's also light, but there is no TV on. So the same thing is with this, and the sum of this load is actually calculated by the right. There is also loss, and the total is by the right hand side. So all the values that are 0 here means that the appliances are not put on at that particular period in time. And where values are included, that means that the appliances are actually on and they are running at that particular point in time. So moving on to the next slide. My colleague will take over from here.
Okay, thank you. This is the load profile. we'll continue from here. Yeah, here shows by my left hand side shows the average daily profile, and it can be seen that its rate is in a kilowatt, and then the load profile, the consumption keeps on increasing from the 0 hour to about 24 hours in a very continuous manner. And then if you check by my right hand side, this is the seasonal daily profile. You see that the increment is inconsistent. Sometimes it goes up, sometimes it comes down, meaning that different season brings out a different condition for the load profile. Going to next, we'll have the renewable resource. The major renewable resource we use is PV, and the data we use were generated from the internet, which is particularly the solar global horizontal irradiance and the area specific temperature, which was downloaded from National Renewable Energy Laboratory, NREL. It can also be gotten from NASA, which is Surface Meteorology and Solar Energy Database, to obtain this data. Now you can see this pie chart. It depicts the monthly average temperature data, and that of the bar chart depicts the average solar global irradiance from January to December. Next, we have the determination of storage technology. So we chose that we're going to use a battery for this storage. Now the battery will serve as a backup system to our system, and that is because we know that there will be a downtime when there will not be access to irradiation. So by then the energy that has already been stored in the battery will be put into use, and that is why we say that battery is standing as our storage component, and it's very, very essential. And this is what we used here. Going to the next one, we'll have the system modeling. System modeling is actually the schematic. It's talking about the architecture, the coupling of all the components. As we can see here, by my right hand side, we have the genset, we have the PV, we have which is the solar panel, we have the converter, we have the battery, and also we have the load, which we have here. So when all these components have been put together, it forms the model that we are using. From what you can see here, the PV type here is the generic flat plate, and the is also rated about 160 kV, and then the rating factor is about 80%. The lifetime is 25 years. The battery storage here is a generic idealized battery, nominal voltage 600, nominal capacity 100, and every other details as it is here. The throughput is also 300,000 kilowatt hour. Going to the next, we have the system continuation of the system modeling. We have that generator is an essential component of our system because it is hybrid anyway. Now we also understand that there will be emission factors, and these are the emission details as you can see here, but we take solace on the fact that we have about 94% renewable coverage, which means that a lesser level of emission will be expected, and it will also serve the people well. My right hand side is the system architecture, which shows all the components and their details. Going to the next, the optimization and the simulation analysis. Now the optimization is basically trying to find the best possible way of this model to operate. Now we talk about both the cost implication, we'll talk about the reliability, we'll talk about the ability of the system to recover money, we'll talk about the return on the investment and the year of the break even. So we'll put all these things into consideration to know if the system is optimal or not. Whereby it's not optimal, we'll revert back to the modeling to change the components to get it well. And the simulation is basically trying to find the best sensitive the best sensitive model that is going to serve the system. From here we're going to see some simulation analysis. this result. But what you see here, you see the optimization result here, and you see the sensitivity cases here. Here we have some sensitivity cases, and it is the sensitivity cases that brings out the best of the simulation that we have done, and it forms the basis for our current model compared to that of our base model. This is what this is talking about. Let's go to the next. We'll see the optimization and the simulation analysis result continuation. Here we'll talk about the generic flat plate, the PV electrical summary. You can see the details, both the minimum output, maximum output, PV penetration, hours of operation, and levelized cost. Then on my right hand side, you see the generic battery result data, and now you can see the whole details and how the expected lifetime, the throughput, the storage, and everything is here. Let's go to the next. Now we have here the renewable analysis result. You see the capacity based matrix and then the nominal renewable capacity. We'll talk about the usable renewable, talk about the energy based matrix, the total and renewable production, and every other details that you want to know about the renewable analysis is written in this left hand side of the table. By my right hand side, you see the generic genset electrical summary. You see the electrical production, the mean electrical output, minimum electrical output, the maximum electrical output. All the details have been written here for our perusal. Let's go to the next. We are here to talk about the financial analysis. Here, it can be seen here that out of the four components, which talks about the battery, talk about the genset, the PV itself, and then the converter, it is shown here that the genset has the highest cost. Anyway, is expected because it is a one-off expenses. It is not what is going to continue over and over again. And then looking at this converter, the converter actually has the lowest cost, which is also expected. And then looking at these, you find out that every other component like a generic flat plate and that of Leonard battery, all these ones have a much more replacement cost and operation and maintenance cost compared to that of generic genset, which means that the one-time expenses for the generic genset is not actually too bad. We go to the next. Now we'll talk about how the system saves money. This is actually a system of a cumulative discounted cash flow. By my left hand, by my vertical side here, you see the cumulative cash flow, which is in dollars, and that of the number of years. And this the system tries to compare a two system. The first one talking about the base model, and the second one talking about the current system. Now the current, we know it's gotten from the sensitivity analysis that we had, and then you can see here that the base system starts from about 100,000 deficit, and then it runs down through that of 25 years, and then that of our current system start about 150,000 US dollars, and it runs down. And then but something very, very special here is that there's a point of intersection, that is when the base system will intersect or be equivalent with that of the current system. Is about the time we'll be breaking even, which is about 4.1 years, as it can be seen here. And then but overall, you see that the current system is better than the base system, which is what we can see here. Next, we'll talk about the nominal cash flow and the discounted cash flow. The nominal cash flow actually talk about the cumulative flow of cash when no expenses or charges have been made, whereas the discounted cash flow is talking about when all the deductions, both the tax and everything that we need to pay, have already been made. And in investment, we see that as the real cash flow, because it has removed everything. We will have removed everything we need to remove, and the remaining is the actual state of the money that we have. Next, we want to talk about the financial analysis. Now we have the analysis of the cash flow. It is clear from our bar chart and the cost type option for this cash flow provided in the economist table that the base model cash flow is almost about 150,000, while the current model cash flow is slightly less than 5,000 minus. Now you can see also from the cost summary analysis that the base model capital replacement, operation and maintenance, salvage, and every other type of cost as listed here. And then talking about the economic comparison, the current model has a net present cost of 331,496, while the base model has a present cost of about $461,884. Then the base model is initial capital is about 90,000, while the current model is about 149,761,000. However, even though that the base model has a lower initial cost compared to the current model, we have seen that the cash flow and the return on the investment made based on the current model will be better than that of the base model. Next, talk about conclusion. Now we want to infer, in fact we can infer from the whole thing we have done that following the simulation analysis that we do and the graphs and everything we have shown here, that the energy demand of 1,200 households in Wamako Town, Sokoto State, Nigeria is about 157.5 kilowatt per day, or roughly about 5,784 kilowatt per year. And then the energy produced by our model simulation, which is the PV and generating set, is about 684 kilowatt per year. More than the town's energy requirements, which means we'll be meeting up the requirements. And then a backup generator is also crucial to prevent a power outage at night. Therefore, PV alone cannot meet this demand. The investment has about 4.1 year payback period and a 21% return on the investment. Although our model contains some emission due to generating set that we have, the environmental impact of this emission is negligible, given that the 94% renewable content is actually guaranteed. Nevertheless, there is always room for improvement. And finally, we are suggesting that government parastatal and every other investor should come and join in financing this project. These are our references as it can be seen here. Thank you.